Thank you for coming to my session, and I start my session. At first, I introduce myself. I'm Chie Hayashida. I'm a software engineer at Cookpad. I'm from Japan, but Cookpad has Bristol office, so I visited for business trip. Currently, I'm working as a machine learning engineer, but my background includes Apache Spark or Apache Hadoop, and I like data engineers. And I'm a contributor of Apache Spark and TensorFlow and so on. And my session is about rather than data engineering and machine learning, but my PyData London session is very many machine learning, so I'm sorry if you don't. Okay, I start. And at first, I'd like to introduce my company. Do you know Cookpad? It can use in England too. It is world's largest recipe sharing platform. So please try it to cooking. Cookpad is global service, and we have Bristol office. It is second largest branch in my company. There are about 250 people working at the Bristol office, and there are about 10 researchers and engineers of about machine learning team. And we are working on NLP, CV, and information retrievals about recipes. It's a lot of fun to cook in the kitchen of the office during our work. Cookpad is used in 71 countries and 26 languages. We have 94 million monthly average users. The photo lower right is a Bristol office members. We are very friendly. I start. My agenda is here. First of all, I explain about why we run parallel and distributed processing. And next, I explain the difference of parallel and distributed processing. And finally, I introduce some popular libraries for parallel and processing in Python and their architectures and features. This is disclaimer. I talked about basic architecture and features of libraries, but I don't talk about the installation and the detailed API usages, because we can easily get knowledge of library usage from our internet documents and any papers, but it is difficult to find a proper document about abstract architectures and how we choose the library for our cases. Yes. Yes, and the first question, how do we decide whether to use parallel or distributed processing? The answer is mainly two. One is that when we use large data which cannot handle us in one process or one machine, the resource which is available in one process or one machine is limited. But if we use more data than the limit, we have to use parallel or distributed processing. It will be able to solve the problem of lack of resource. The second one is that when we run program in short time, even if we can use large data in one machine, if it often occurs that the job time is too long. In such case, parallel and distributed processing will be very useful to short the job time. So I say that large data, but what is large data? I drawn 3 patterns. One is 100 million megabytes, and 10 gigabytes, and 1 terabyte, which is the large data. In fact, it is case by case. Because the word large is a relative word. If I take example with current technology, we use pandas data frame for machine learning or machine learning data engineering, but the pandas data frame works most efficiently with less than 1 gigabyte data with user machines. Before parallel and distributed processing, how about scale-up? Scale-up can solve lack of resources too. Especially with cloud services, it's very easy to expand machine resources with GUI or AWS or GCP. It is very easy, so, easier than parallel processing or distributed processing. But there are problem in scale-up too. First, we sometimes be not able to use full of machine resources with one process. When we run one Python process, we can use only one CPU as default. So there may be many CPUs and a lot of memories in machine resources, but the problem cannot use efficiently those resources, and most resource status is await. Second, the resources that can be mounted on one machine are limited. There are high-performance PC, but it's very expensive and very rare. So when we can't expand resources more, we should consider scale-out with distributed processing. So let's learn parallel processing and distributed processing to process large data efficiently. In fact, parallel processing and distributed processing is not the same. So next question, can you understand the difference of parallel and distributed processing? Can you answer? No? No? Please. No? No, can you? No?
Should I explain it now?
Okay.
Yeah, I think I can.
Okay, so answer is here. We often use these two words as same meaning, but they're not same. Parallel processing is mainly for only one machine, and parallel processing use multiple processors and sharing memory. On the other hand, distributed processing aims at the possibility of sharing the processing by exchanging data through messages between multiple machines. So we use resources which are physically separated. Yes, and next, I introduce the library to the. I introduce the library about parallel processing and distributed processing. first, I introduce about parallel processing libraries. The first is threading and multiprocessing. Python has official modules for parallel processing. Python is often said that a battery included. It means that Python itself can use various functions without third-party libraries. So we can use parallel processing without third-party libraries. Threading. I explain about threading. Here is the image of Python's threading architecture. When we run Python programs, the program has one main thread as a process. When we use threading libraries, we can use subthreads for parallel processing. The thread number is parallel number. So in this image, the program creates two subthreads for parallel processing. But in threading, there is GIL limits. For GIL environment, only one thread can use CPU at the same time, even if the program has 2 or 3 or more threads. So Python threading is in fact not parallel, but it's concurrent from aspect of CPU execution. But why GIA is used? CPython interpreter does not implement mechanisms of synchronization for the concurrent access by threads. So there isn't GIL in JSON and IronPython or another distribution of Python. Currently, PEP 554 proposes a sub-interpreter to obscure GIL. I think about in Python 3.8, I think. But in what situation is threading effective? So threading cannot use CPU in parallel, but we can use I/O processing during another threading using CPU. So this is I/O processes. So it's effective for I/O-bound programs such as read-write files or DB connections or download data from networks. CPU usage cannot duplicate, but I/O process can duplicate between 2 or 3 threads. But if we use too many threads, there occurs many context switch which decrease performance. So we should be careful to increase the number of threads. Next, multiprocessing. Multiprocessing spawns a process for parallelization. Multiprocessing library parallelize in both local and remote machines. Let's study more about how multiprocessing divides one process to sub-process. With multiprocessing library, each process has its own memory spaces. It's different from threading, which shares a memory in multiple threading. So it's not affected by GIL, and less likely to cause error due to race condition, data corruption, or deadlock. In what situation is multiprocessing effective? Because of such a feature, multiprocessing is effective at tasks which is CPU-bound, such as numerical calculation, matrix manipulation, or regular expression processing. But the performance in Python's multiprocessing doesn't increase linearly because there are overheads. what is overhead? Also, there are several OS functions to achieve multiprocessing. Python's multiprocessing library uses OS fork function. OS fork function copies necessary resources such as memory spaces from parent process to child process. So, for example, when memory size of parent process is very large, there is overhead due to communication between parent process and child processes, children processes. And one more overhead. There is another point to take care. Text which can learn at same time is limited to the number of CPU attached on the machine. So when we learn 6 tasks on the machine, which has only 2 CPUs, two tasks run at first, and after finish those tasks, another task will start. If you'd like to increase the number of parallelism, you have to increase CPU number of machines. Next, I introduce about joblib. Joblib can use threading and multiprocessing libraries function more simply and functionally. Joblib's default backend is Loki, which is the third-party parallel architecture, but we can use threading and multiprocessing very easily too. And Loki's algorithm is very similar to multiprocessing too. Joblib has a lazy evaluation function and can use transparent disk caching of the output. Calculations are performed as needed by the outputs and only when its inputs change. Joblib can written very simply and easily than threading and multiprocessing. It is truly recommended for users of threading and multiprocessing. Last feature is that logging. We can use logging and tracing of the execution with joblib. So we can debug our processes easily with joblib. Summary up to here. Python has official modules for parallel processing. Threading is effective to I/O-bound processing, and multiprocessing is effective to CPU-bound processing. Both of two are mainly only for processes run at only one machine. We can use threading and multiprocessing functions with joblib more simply, and some of data libraries transparently use these parallel processing libraries. For example, NumPy is multi-threaded using BLAS or C implementation. When we run TensorFlow with CPU, TensorFlow is multiprocessed using backend implementation. And scikit-learn depends on joblib. So we, in fact, use parallel processing consciously. The next is distributed processing. We finally got the distributed processing. It was very long from the session started. Please remember distributed processing architecture. When we have to use distributed processing, we have to consider about distributed processing when we use large data which couldn't process in one machine. And I introduced 3 libraries. One is Celery, one is Dask, and finally PySpark. Celery is the distributed task queue built in Python. Celery's feature is here. Celery has simple and flexible architecture, and every path can be extended. Heavy use for task-based workload is in Python. For example, Django backend or Airflow backend. Celery's architecture is here. Celery have several components. A worker will run its tasks and store the results into the backend results store. So when we run a job at client, the application will be sent to broker, and broker has several queues. So the application will be sent to one of the queue. So queue will send the application parallelize and sends the application's tasks to several workers. Workers will run tasks and save the result to backend storage. In what situations is Celery effective? When the task Celery is effective when the task is simple, but the amount of data is too much for one machine. When you want to use it with another framework such as Django. Since Celery is a very simple task queue system, simple task but the amount of data is big for one machine will suit for it, but when you try to run complex tasks on Celery, you have to write a lot of code, so it is not so good, recommended. Next is Dask. Dask is distributed processing framework built in Python, a pure Python library. Dask is able to use NumPy, pandas, race-like parallel objects. It is named as Dask array, Dask data frame, and Dask bug. Dask has on scheduler. Scheduler is customizable to get good performance from both for parallel processing and distributed processing and on cluster. Dask has good web interface for real-time job monitoring. This is Dask scheduler. When the Dask application runs, the object is array, bug, and data frame. We use this object for our code, and the Dask will generate task graphs to run the parallel processing, and scheduler will use synchronous threads and multiprocessing or distributed. Dask interface is very beautiful. So we can debug or tuning our programs easily with this UI. But in fact, situation is Dask effective. Dask is effective when we want to parallelize NumPy or pandas processing. When the data size fits, Dask is effective when the data size fits 1 to 4 or 5 machines. Finally, I introduce PySpark. PySpark is built in Java and has Python interface. PySpark can be made more scale out than Celery or Dask. PySpark is originally built to run on Hadoop cluster. PySpark has very many implementation, but the performance tuning, so the PySpark is fastest and most cost efficient in very huge data. So, and PySpark also has good web interface such as same as Dask. And PySpark can be easily write complex program with rich operators. PySpark has a Stream API and machine learning API, so we can implement very many type of codes. We can use PySpark with management service as in cloud service, such as AWS or AWS EMR or GCP. It is PySpark architecture. Spark is built with Java, but we can use Python operator. When we use Python operator, the Python code data will be picked and Py4j will transfer the data to the Spark's data architecture and send to worker. It is a scale of Celery and Dask and PySpark. We can use Celery and Dask for one machine to 4 or 5 machines. But PySpark can be used in 1 to thousands nodes. So PySpark can use very, very huge data, but Dask or Celery can't use so huge data. So in fact situation is PySpark effective. When we want to run, PySpark is effective when we want to run complex tasks with a large amount of data. When we and if we use Hadoop cluster, PySpark is recommended. Overhead of parallel distributed processing. I introduced distributed processing, but distributed processing is not so. It's not silver bread. So we have overhead. So if we use small data, distributed processing is not recommended. That's wrong. It's time. Conclusion. We can use machine resources efficiently and speed up our program with parallel distributed processing. There are several parallel processing libraries available in Python. I recommend Joplib for general usage of parallelism in one machine. I recommend Dask for parallelized pandas data frame program. I recommend PySpark for huge data which cannot handle in one machine. Don't afraid to use parallel or distributed processing more. Thank you very much.
It seems like what you talked about of libraries work well when you have kind of embarrassingly parallelizable tasks, but what about message passing in Python? Is there any kinds of...
I'm sorry, can you...
Are there any libraries you might recommend that have like message passing capabilities?
You mean MPI?
Yeah.
MPI is row-level API implemented in C, and MPI is MPI means MPI has two means. One is protocol for message passing, and second is library name. The library is OpenMPI or another MPI libraries. They are mainly implemented in C and very low level implemented. So distributed, when we learn distributed processing, the framework should have the partition tolerance functions or backup and recovery system and retry system, but native MPI system library don't have that functions. But MPI is very fast. So we can't compare to Python's PySpark or Dask's to MPI. It has good point and bad point. Okay.
More questions?
Thanks for the talk. You said at the beginning that multi-threading is particularly useful for processes that are I/O bound, right?
Yes.
Isn't that always the case? I mean, you know, isn't general parallel processing always useful for I/O bound processes, not just multi-threading?
Sorry, threading and I introduced threading and multiprocessing. And threading is for I/O bound processes, and multiprocessing library is for CPU bound processes, because the threading cannot use a CPU duplicately. Could I answer you? No?
You?
Maybe we can take it offline then.
Thank you.
More questions? Thank you very much to the speaker.
Thank you very much.